Thank you for inviting me to the Robust Vision Challenge workshop at ECCV 2020. My name is Girshick, and I'm a research scientist at FAIR. This talk will be about an axis of evaluating robustness that occurs naturally and is at the heart of what it means for machines to have visual intelligence. This axis is what I'll call data abundance. It's the fact that some visual concepts occur frequently, while others are rarely seen. Yet, we want our models and algorithms to perform well across this entire spectrum. This talk is based on joint work with Agrim Gupta, who's now a PhD student at Stanford, and with Piotr Dollar, who's a research scientist at FAIR with me. I'll start with a story about how I came to work on this topic and build a new object detection dataset called LVIS. There are many different axes along which one can measure robustness. For example, the current set of tasks and datasets in the Robust Vision Challenge do a nice job of emphasizing what's often called the domain of the data. For example, COCO web images versus mapillary street images. Or, within the street scene domain, another axis to consider is different weather conditions, such as sunny versus snowing. It is important that models and learning algorithms are robust to these different data distributions. A different axis that I've been particularly interested in for several years is what I'll call the data abundance axis. Most computer vision data sets these days are of course large, but in addition to that, they also have a lot of training data for every single category, typically hundreds or thousands of examples per category. Current deep learning methods can work well in this case. However, things start to look quite different when the number of training examples per category falls to just 10 or even fewer. In this regime, deep learning models start to falter. Of course, there's a whole literature now devoted to this problem. It's called few-shot learning. I got interested in this area back in 2016 and was immediately struck by the fact that while the rest of computer vision was using challenging data sets, the few-shot literature at the time was working on omniglot or miniaturized version of ImageNet called mini-ImageNet. The evaluation protocol that was established made few-shot learning its own separate world. The assumption was that all that mattered was few-shot learning performance, and it was irrelevant how well the proposed classifier would work on categories with abundant data. This struck me as the wrong way to frame the problem. It was also against the notion of learning systems that are robust to the data abundant spectrum. Of course, a model and learning algorithm should work well when given little data, but it should also work well when given lots of data. It was difficult to understand if models and algorithms were in fact robust to data abundance because the research world was fractured into two camps. In Camp 1, in the upper left of this figure, which I'll call papers on the standard classification setup, you'd see results on standard data sets for which all classes have lots of training data. In Camp 2, the bottom right of this diagram, you'd see results on specially crafted few-shot classification data sets, in which you'd see accuracy for categories with few examples. These datasets were different, and the models and learning algorithms used for them were also different. It was impossible to compare and understand what was going on across these two camps. Now, what is the secret x-axis in this plot? You probably have a guess already, but I bet that you're wrong. What we found instead is that if you benchmark few-shot learning algorithms in a setting that measures accuracy on categories with many examples, as well as with few examples, there's typically a trade-off. Methods that were developed for few-shot learning were tuned in ways that actually hurt their performance when lots of data was available per class. On the flip side, tuning the algorithm to recover accuracy on the classes with many examples would then hurt accuracy on the classes with few examples. In general, you find a trade-off curve that looks like the one above. As an algorithm is tweaked to work better on few-shot learning, its performance when many examples are available drops. Bharath Hariharan and I developed and tried to promote a new benchmark that would test robustness to data abundance by measuring performance on classes that have lots of data, as well as classes that have very little data, in order to explicitly explore this trade-off. Of course, this diagram here is just a cartoon illustration of the observed trends. You can refer to the paper pointed to above for the actual experiments and data. Now, despite our best efforts, we were unable to persuade the few-shot learning community to adopt a robust evaluation perspective. And still, most few-shot learning evaluation is performed in this non-robust setting where one assumes that all classes have little data, and performance when a lot of data is available is irrelevant. Now, to be fair, the setup that we proposed back in 2017 was overly complex, and the few-shot learning community already had significant momentum that we were trying to overcome. So we needed to offer something better. So after that experience, I went back to the drawing board and hatched a scheme. The idea I schemed was to take an existing community that is passionate and cause them to work on few-shot learning, even if it's not their primary concern. And the key to this plan is that few-shot learning is not some niche problem. It's actually completely fundamental to all learning. Visual concepts are observed with different frequencies in the natural world. Some things are just simply rarely seen. The rest of this talk will be about building a new data set for the object detection community that expands research in a very natural direction. That is, with the goal of simply trying to recognize more object categories. But in doing so, it will naturally cause researchers to work on few-shot learning and to evaluate their methods in a robust setting. How this naturally happens all starts with the naming of things. Why do we want to name things? We name things in order to communicate. Obviously, this could be human-to-human communication. I ask for a wrench, and you know exactly what to hand me. But even more so in the future, it will be for human-to-machine communication. I ask my robot helper for a wrench, it looks at the environment around it, sees the wrench, and then hands it to me. If we expect automated systems to do many things in the world, they will need to have a vast vocabulary that can cover a wide range of situations. To illustrate this point, we can consider this image in more detail. In fact, we'll play a simple game. First, we'll mark an object in the image that's not already marked. Then we'll name it, and then we'll mark all the instances of it. And then, if there are no more unmarked objects, we're done. Otherwise, we'll repeat this. First, we see a car, because it's the largest, most salient object. Then, a wrench. We mark all the instances of the wrench. Then we see a bag, some bolts, an oil spray can, a car door handle, a cell phone, and so on. There are many things in this image, and we might ask an autonomous system about any of them. Our goal in the LVIS project was to provide a dataset and benchmark for research on this scenario. We want to take the field of object detection from the world of COCO with its 80 categories into the future where detectors will be able to detect thousands of different object categories. That is, we want to support the task of detecting everything in an image. On the surface, this might appear to be just about increasing the number of classes that a detector outputs. However, it exposes fundamental new research problems, and I'll spend the rest of the talk talking about two of these: benchmarking and data-efficient learning. The benchmarking problem is all about how you define the detect everything task in a way that leads to tractable data annotation and fair evaluation. This is incredibly important because evaluation is how our community makes progress. For more insight into this, I recommend reading David Donahoe's 50 Years of Data Science and learning about the Common Task Framework. The second problem is about data-efficient learning. When a dataset contains a large number of categories, it will naturally contain frequently occurring categories, as well as a long tail of rarely occurring categories. And as we know, if categories have relatively few examples, accuracy of existing systems drops to very low levels. For example, if we reduce the COCO training data to 1,000 images, then AP, or average precision, for this particular detector drops from 36 to just 10. And this is a case in which 90% of the categories still have more than 20 examples, which might not even be considered low-shot learning by many people. Let's jump into problem 1, benchmarking. In order to make progress on the task of detecting everything, we need a suitable dataset for benchmarking. For that, we've introduced the LVIS, Large Vocabulary Instance Segmentation Dataset. We released a preview version of it at CVPR 2019, and I'm happy to announce that we released the final v1.0 release of LVIS back in June at CVPR 2020. LVIS now contains 160,000 annotated images, just over 1,200 categories that were discovered using the object spotting game that I showed you earlier, and just over 2 million instance segmentations. And due to the object spotting process, the dataset naturally contains a long-tailed distribution of object categories. I refer to this kind of data as big little data. It's big because it has a large number of annotated objects. In fact, it has 67% more annotated objects than COCO does. However, it's also little because there are a large number of categories that have relatively few training examples. Now, building LVIS is actually its own research challenge. LVIS is unlike previous detection datasets. I'll claim that PASCAL and COCO were relatively easy to build in the sense that the data collection steps were pretty well understood. In particular, they started with a hand-selected set of categories that were chosen prior to image collection. Images were then collected by searching for these selected categories. This process means that categories can be well separated by design. There are few or no ambiguous cases. For example, no one will ever confuse a potted plant with a sofa. This design also means that annotating all instances of the small number of categories, a property that I'll refer to as exhaustive annotation, is easy to do. However, in LVIS, all of these nice properties go away. At the scale of thousands of object categories, the boundaries between categories can get fuzzy. Now, an NLP researcher once told me, the thing that computer vision people don't get is that the entity in the image is not the label. The label is just a referring expression. What this means is that for a given object or entity in an image, there are multiple valid ways to refer to it. That is, the category is a referring expression, and therefore an object may easily belong to multiple categories. For example, an object such as a toy deer may be referred to both as a toy and a deer. Cars and trucks are both vehicles, and backpack and rucksack are synonyms. If one were to try to build LVIS the same way that COCO was collected, it would require making more than 1,000 forced binary judgments for every object in every image. This is a non-starter because the volume of annotation work is too great, and the multiple referring expression issue will undoubtedly lead to many errors and inconsistencies in the annotations. The fact that we're dealing with referring expressions helps us understand a bit more deeply why object categories are fuzzy. It's fundamentally because people will disagree on how to refer to some things in the world. There are a lot of funny examples of this, such as an article in the Washington Post about the debate over if a hot dog is actually a taco or a sandwich. Or this article on Vice.com asking the eternal question of if cereal should be considered soup. While those might sound silly, a real example that I encountered is toast. It's easy to find bread that has been heated to a crisp and used in different contexts. So here on the left is something that I would consider very easily and clearly to be toast, probably because it's being served in the context of a breakfast. On the right, you also have bread that's been toasted to a crisp, but it's being used in a sandwich, so it doesn't feel like toast anymore. And then you have some examples in the middle. And here it becomes pretty unclear to me whether or not these should be considered toast. So we face many problems. How can we build a dataset that allows for multiple categories per object when facing the fact that exhaustive labeling is prohibitive with respect to both time and money? And additionally, exhaustive labeling does not necessarily make sense because many object categories are actually fuzzy. For example, the case of toast on the previous slide. But if we do not have exhaustive labels, is it even possible then to evaluate average precision of an object detector? And if we can't do that, then what's the purpose of the dataset? Amazingly, all of these problems are elegantly solved using a new way to structure object detection datasets that I call a federated dataset, which is not to be confused with federated learning. A federated dataset is a single dataset that is composed of the union of many smaller datasets. In this figure, the overall dataset D is shown as the union of smaller datasets, one for each category. Each category-specific dataset consists of positive images for that category and negative images for that category, indicated with the pluses and minuses. The same image may be shared between multiple per-category datasets. In fact, these per-category datasets heavily intersect each other in practice. This structure will provide sufficient conditions for computing average precision, which is the standard way that object detectors are evaluated. To see that, let's look at the guarantee provided for each category level dataset. So for category C, we have positive images in which all instances of category C are exhaustively labeled. And we also have negative images for which we guarantee that no instances of category C exist. Then there are all the other images in the dataset D. These images are unknown with respect to category C. The positive and negative sets are sufficient for computing AP for category C. During evaluation, the unknown images play no role in the evaluation for this category. Importantly, on the val and test sets, the positive, negative, and unknown membership is hidden, so the detector must assume that all images are labeled with all categories and try its best to output the objects that it thinks it's found. Federated dataset design has two nice properties that make building datasets like LVIS tractable. First, because the category level positive and negative sets can be modest in size, this dramatically reduces the cost of labeling. Second, there is no forced choice when labeling objects. If an annotator cannot tell what label to apply to an object because it is on the fuzzy boundary between categories, then it can simply be left as unknown without creating a problem for evaluation. To collect this type of federated dataset, we used a custom 6-stage annotation process. It starts with the object spotting game I showed you earlier, in which objects are spotted in stage 1, and then all instances of spotted objects are labeled in stage 2. Then, in stages 3 and 4, we perform instance segmentation and quality verification, going back and forth until all instances have been segmented up to a certain level of quality. In the 5th stage, we check images to make sure that positive images are actually exhaustively annotated. If any case is found with missing annotations, for example, a missing book in this figure, then we flag that so it can be handled properly during evaluation. Finally, we collect a set of negative labeled images for each category. This process results in pairs of images and categories like these shown here. For example, This is an image that contains 2 beer kegs. They are not the most notable or salient objects in this scene, as you would typically find in many previous detection datasets. Another example, here are lanyards, like we would be wearing if ECCV were a physical meeting this year. And finally, one example to show off the quality of the segmentations that we've collected. We see the fine detail captured in the pineapple segmentations. In fact, LVIS segmentation quality is very high. We compared segmentation mask quality using 2 metrics, mask IOU and boundary F measure, between the collected dataset annotations and annotations performed by highly skilled experts using Photoshop. This experiment demonstrates that LVIS has much higher quality segmentations than COCO, and this is particularly true for object boundaries. We also ran our data annotation process twice on a set of 5,000 images. For each image, we can match objects across the 2 annotation runs and compute the F measure for each category, indicating the degree to which the separate annotators agree on the naming of each object. We see that for more than 70% of these image category pairs, that there's perfect agreement, and overall the average F measure is 87%, which indicates that the naming process is largely repeatable and not subject to high degrees of ambiguity. Now I want to transition to the second problem, which is data-efficient learning. After years of making AP high, the LVIS dataset will make AP low again. To recap, LVIS has a large vocabulary of objects that were discovered in images. This process starts from a set of images without knowledge of what categories exist. It discovers the categories, and in doing so, it uncovers a long tail of rare categories. We can visualize this process by looking at how the number of categories increase as more and more images are annotated. As expected, when images are first labeled, a large number of categories are found right away. And as the process continues, this starts to plateau. However, because we keep adding more categories as more images are labeled, this long tail is essentially inescapable. Now, you might try to get around this issue by simply adding more images that contain instances of a category with few examples. However, if you continue to play the game that we outlined earlier, you must also label all of the other objects in the images that you're adding, and this will simply introduce new rare categories over time. To illustrate the challenge posed by LVIS, we can look at what happens when you train a strong baseline detector on it. In this case, I'm using MaskRCNN that has been trained with a 2-stage training strategy. In the first stage, it's trained as MaskRCNN normally would on a standard dataset like COCO. In the second stage, the network weights are frozen, except for the final linear layers that perform classification, box regression, and mask prediction. These linear layers are then trained again using a data resampling strategy. The resampling strategy picks a category uniformly at random and then an image that the category appears in, again uniformly at random. This 2-stage technique was recently shown to provide a very strong baseline for few-shot learning. To evaluate systems on LVIS, we look at overall AP as well as AP broken into 3 buckets based on the frequency of the categories in the training data. We call these AP rare, AP common, and AP frequent. Now, tying this back to the intro and to the theme of the workshop, I want to point out that by disaggregating the overall AP metric into metrics that focus on different category frequencies, we see that LVIS is a kind of robust vision challenge in itself, pushing for robustness along the data abundance axis. To do well, it's necessary to improve in the few-shot case as well as the many-shot case. And as you can see, for rare categories, average precision is at only 60% of the AP for frequent object categories, indicating that there's still a lot of work to do in order to close this robustness gap. While on the topic of evaluation, I want to use this opportunity to discuss some important issues around evaluation and the best practices to address them properly. It's important to understand the noise characteristics of evaluation. In this experiment, we trained the same model configuration 50 times, allowing only the random number generator seed to change between experiments. We then computed the standard deviation for the 4 AP metrics. For overall AP, the standard deviation is fairly low, 0.2%, although it's still 2x higher than the corresponding value would be for COCO. For AP rare, take care to note that the standard deviation is nearly 4 times higher than it is for overall AP. Since rare categories have few examples for training and also for evaluation, it is natural that there will be more variability in this statistic. Based on these observations, we make the following recommendations as best practices. If possible, please do try to run each experiment multiple times and report the mean and standard deviation. A 1% absolute change may be a significant result for AP common, AP frequent, and overall AP, but it is perhaps not likely to be significant for AP rare. Do not train and report the single best result from multiple runs. This result will definitely show overfitting, and it will not translate to the test dev or test challenge sets. Finally, always please specify the experimental protocol. For example, you could state that you ran each experimental configuration 5 times, changing only the random seed, and then report the average result and standard deviation. So in summary, I've covered the new LVIS dataset. We've just released version 1.0 and are looking forward to seeing what the research community is able to do to come up with new techniques to tackle the challenging problem of learning from few examples. And on that note, I want to end by advertising the LVIS Challenge that we just held in conjunction with the COCO workshop at ECCV a few days ago. Given the tight timeline and current events, we had impressive participation and saw some really amazing improvements in the results. You can find out more information, including downloading the tech reports from the entries, at elvisdataset.org. Thank you.